Modern calculus, at least at the level we'll discuss in this class, is generally divided into two main parts, differential calculus and integral calculus. Differential calculus is the calculus of rates of change. A rate of change simply tells us how fast a quantity changes with respect to another quantity. We see rates of change in the real world all over the place. When we're driving a car, we use miles per hour to measure the speed of the car. Or in physics class, you might measure speed using different units, like meters per second. A speed of 45 miles per hour means that if we continue to travel at that speed, we will go 45 miles in 1 hour. A rate of change is almost always a ratio of quantities with units that are also a ratio, like miles per hour. Some other rates of change that you might see around you include dollars per gallon for the cost of gas, miles per gallon for measuring the efficiency of your car, inches per hour for measuring how hard it's raining, any kind of cost per unit like dollars per ounce for the cost of items at the grocery store, miles per hour per second to measure the acceleration of your car or how fast your speed is changing. In physics, we typically measure acceleration in meters per second, or meters per second squared. Any of these rates of change are things we might study in differential calculus. In previous math classes, you have been able to use data to calculate average rates of change over a given time interval. For example, if I told you that I traveled 180 miles in 2 hours, you could calculate my average speed over that 2-hour period, which would be a speedy 90 miles per hour. The problem with this average rate of change is that it gives me a general picture of what happened over the 2-hour period, but nothing about what is happening at any particular time during those 2 hours. I could achieve this average speed by driving a constant 90 miles per hour the entire time, or by driving variable speeds while still covering the 180 miles in 2 hours. If we look at data for these rate of change problems on the coordinate plane, then finding an average rate of change is equivalent to finding the slope of a line through 2 points. For average rate of change problems, the line we find the slope of is called a secant line, meaning that it is a line that intersects a curve in at least 2 points. However, if we want to know a speed at a particular time, the kind of problem we'll study in calculus, we'll want to find the slope of a tangent line, or a line that touches a curve at a single point without necessarily passing through it. We'll discuss exactly what it means to be tangent later. Finding the slope of a tangent line can get a little tricky, since we want to find the slope at a single point, but using the slope formula requires 2 distinct points. Differential calculus is motivated by what I will call the tangent line problem, and it's the study of instantaneous rates of change. While differential calculus deals with rates of change and slope in the coordinate plane, integral calculus deals with finding areas in the coordinate plane. Like differential calculus, it is not as simple as using formulas and ideas that we have in the past. If you think back to your geometry class, you might remember formulas for finding the areas of rectangles, trapezoids, triangles, and circles. But instead, we'll want to find the areas of regions that are bounded by curves, such as parabolas or trig curves. But there were not simple area formulas from geometry for finding the areas under a parabola or under a sine curve. Also, like differential calculus, making this measurement on the coordinate plane translates to actual measurements related to the graphed function. For example, if you were to find the area of a region bounded by a function that represents the speed of a car over some time interval, that area would give you the distance traveled by the car during that time. If a car is driving at a constant speed, there's a simple formula that tells us how far it travels. Distance equals rate times time. We can see on the coordinate plane how this might correspond to an area, in this example the area of a rectangle. However, if the car's speed is changing, then computing the area suddenly becomes much trickier, and we now have a need for methods of finding areas that we did not learn in geometry class. This is what I will refer to as the area problem. A vast majority of the topics that we'll discuss in this class will fall into one of these two categories: differential calculus, which is motivated by the tangent line problem, and integral calculus, which is motivated by the area problem.